This video is for the final lesson for Chapter 6 for Physics 12. We're going to take a look at something today called terminal voltage. We're actually going to see a few different little vocabulary words come up today. One of them is going to be this little phrase EMF, and we'll also see something called internal resistance. And here's what the lesson is all about. It turns out that all real batteries, all real cells in real life, unfortunately, it's not ideal, but unfortunately, they all have at least a little bit of what we call internal resistance, resistance on the inside of the battery. Again, it's not something that we want to have happen. It's just a kind of a consequence of the way that they're constructed. They don't perfectly allow circuits or currents to flow through them, and we do get a little bit of resistive losses inside the battery. Now, we have always talked about a shopping analogy for our electric circuits, and I want to tell you what the shopping analogy would be for this internal resistance. Imagine one day you wake up, you've got a big shopping day planned, and your plan is to go and hit the bank, get some cash, because you're going to go off to a market. That way you can go and use that cash to go and buy something. So you've got no cash in hand, right? You start with nothing before you go into the battery. So you go into the bank, you go in the indoor. Looks like a nice bank inside. This is where you're going to get the energy, where you're going to get that money. So you wait in line, you walk up to the teller, you have a great conversation about how you're going shopping today, and you need some cash, and the teller's quite helpful and says, "Oh, okay, I'll check your account. Yeah, you've got enough in there. I'm going to give you the cash." And so they pass you the cash, and then you're like, "Great. That's what I needed the bank for, just to give me the money, right? And now I'm going to leave the bank and then go and find a store to do some buying." So you're heading towards the exit of the bank. You haven't even got out of the bank yet, right? You're still inside the bank, haven't even got to the exit door yet. You're in a really big hurry, so you're kind of running because you got a big day of shopping on the go, right? So you're kind of running for the exit door, right? Like, oh yeah, I got to get going. And before you can even get out the exit, boom, there they are, Girl Guides. They've set up a table on the inside of the bank. This is unheard of, that there's a store in the bank. And it's not any old store. It's a physics, electric circuit store that you have to go by. So they're sitting there with their little table by the exit door, and you are a customer. And you might be thinking, well, I don't want to buy the Girl Guide cookies. No. You have to buy the cookies, right? That's how the deal works. In order to get through the store, you have to make a purchase. And so you're actually obligated to buy some of this product, these Girl Guide cookies, before you've even left the exit door of the bank. So by the time you get out the exit door, you will not have as much money as you had at the teller. You get that money at the teller, that's what we're going to call the EMF, and then you spend a little bit at the Girl Guides. Now, backing things up, the more you're in a hurry, the more the Girl Guides are going to want you to buy the cookies, right? If you go slow, you don't have to buy as many cookies, but to get good service, to get through that store, you have to spend some money. And the more money you spend, the faster you can get through. So if you want to get through fast, you have to spend more. And that's all before you even make it out the exit door. So can you draw like both of these circuits here? On the left, we're going to draw the Physics 11 ideal version where the batteries had no resistors on the inside. And so that rectangle is going to represent the battery. It's going to represent the bank, if you wish. The two lines, one larger than the other, represents that voltage you're going to receive because of the chemistry. And then in the right-hand side of the story, we've got the real picture where there actually is a little bit of resistance there. It's not a lot, so maybe we'll use lowercase r, but it is there, and you're going to have to spend some money to get through that before you can get out the door. Now, outside that battery, I might connect up maybe a light bulb. Maybe this is from a flashlight, so I've got my what we call load resistor on the outside. That's probably a bigger resistance than the internal one, so I'll call that capital R. And on the left side of the page, the grade 11 world, there just wasn't a resistance on the inside of that battery. But in the real life world that we can deal with in grade 12, there is one there. Turns out that resistance is kind of like right on top of that transaction at the teller. But usually we draw it either before or after those lines. Not on top, it would be kind of a mess. So some vocabulary. The letters EMF are actually an abbreviation for electromotive force. And it might sound like it should be measured in newtons, but it's actually a voltage. It's the original voltage that you get from the chemistry. If you want to rewrite that without using all three letters, EMF, you can write it as just a capital E as long as you draw it as like a script E, right? Kind of a nice dainty looking E, then that can abbreviate the EMF, which is already the abbreviation for electromotive force. And that comes from the chemistry. And if people say, oh yeah, it's a 9-volt battery, they're talking about the EMF value. The little r is going to be that internal resistance, the amount of resistance that you're obligated to go through before you can get out of the bank. It's the Girl Guide store. The terminal voltage will be the amount of voltage that survives leaving the battery. So that's money you get from the teller, and then subtract money you have to spend to get by the little Girl Guide store. That's how much you'll have left as you leave the bank and are about to go into the community and do some shopping. Now let's go through an example here. We're just going to do this side-by-side example and then one additional one. But for this first example, let's compare the ideal grade 11 world where there was no resistance on the inside to the grade 12 one. So the story will be chemistry voltage of 6, a light bulb on the outside that's 4 ohms, and then in the grade 12 version, we'll also put a resistance on the inside of 0.8 ohms. And on the grade 11 story, we'll put it on the left, we won't have any internal resistance there at all. So much like the top of this page, I'm going to split my page for the notes for a little bit. Encourage you to do the same thing. Where on the left, we can put the ideal world with no internal resistance, and then on the right, we can put the real world. And we'll see how they're a little bit different. So again, on the left is the grade 11, and on the right is the grade 12. So the grade 11 world, you would say there is only one resistor in this story, just the light bulb. It's outside of the battery, it's 4 ohms. But in the real world, we would go, no, it's a series circuit, right? Looking back, it's a series circuit with the 4 ohms on the outside, but that's in series with the 0.8 ohms on the inside. So actually, the electricity needs to go through 4.8 ohms in order to get through the circuit. Okay, the current. The current in the grade 11 world would just be our 6 chemistry volts, the EMF divided by the 4, 1.5 amps. But actually in real life, it's a little bit less than that. The little Girl Guide store kind of slows the economy down just a little bit, right? It's going to be 6 volts divided by 4.8, so only 1.25 amps flowing there. Now let's ask the question, how many volts would you lose because you're shopping inside the battery? On the left, in the grade 11 world, you would go, what are you talking about? You don't lose money in a battery. And I would say that that's true for grade 11, but in grade 12, no, the little Girl Guide store is there. And if we just do V equals IR, we can talk about the main I, because the Girl Guides are smart. They're putting their store right on the main branch of traffic. They're going to have 1.25 amps going by, but they're only 0.8 ohms of resistance. And when I multiply those together, I got a 1 volt drop, like a $1 drop. So in this story, you're going to the teller, you get $6. You make your way to the exit, the Girl Guides are there, and they're like, nope, you have to buy $1 worth of cookies, right? So you get a small little handful of cookies for $1, and you leave the bank with only $5. Okay, so that's the terminal voltage. In the grade 11 world, you'd be leaving with all of your $6. But in the grade 12 world, here's kind of our main equation of the day. The terminal voltage is the EMF, the chemistry voltage, minus the loss to the internal resistance. So 6 minus the 1. For only 5 volts. And that's what you would be measuring with a voltmeter if you attached it to the terminals of the battery. You'd be measuring how many volts actually make it out. Okay, at the light bulb, what's going to happen when you try to light it up? We're now outside of the battery. We're outside of the bank. 4 ohms. In the grade 11 world, you've got 6 volts pushing and 1.5 amps flowing. In the grade 12 world, now there's only 5 volts left and only 1.25 amps flowing. If you want to find power, there are so many options for finding power, and they all give you the same answer. We can go I times V, or I squared R, or V squared over R, and I can do that trio of calculations for the grade 11 world, and I get one answer. I can do it for the grade 12 world, and I get one, but different answer. So there are the values for both the grade 11 and grade 12 worlds, and the numbers. When you actually try this out, in the ideal cell, it's 9 watts. It'd be a pretty bright light bulb. But in the real life cell, where you actually had some losses happening inside the battery, there's actually only going to be 6.25 watts from that light bulb, so it's a little bit less. Now that resistance on the inside does cause the battery to get warm. So when you really run that battery hard with a lot of current flowing through it, that little loss in there will create some power lost on the inside. It doesn't even make sense to do this calculation in the ideal world. The power loss would be 0. But in the world of internal resistance, we can do IV, I squared R, or V squared over R. But we have to use numbers specific to the little Girl Guide store. How much current flows by? How much money are they taking from the customers? Right? We can do that. Or we can go the current squared times their resistance, or the voltage lost by the customer squared divided by their resistance. And so you've got 3 options, and putting the values in, it would look like that. 1.25 times 1, or 1.25 squared times 0.8, or 1 squared divided by 0.8. All of those give you this value of 1.25 watts. That battery is going to get hot, right? It's going to be giving off some heat, 1.25 watts of heat while it's running. Now, along the way, we had to know that there was a current of 1.25 amps. And I want to show you some options for how you can find that current, because you need that current to use this main equation of the day, that the terminal voltage would be your chemistry EMF minus the loss from the Girl Guides. So here are some options for finding this total resistance. I'm going to show you 3, one of which is very uncommon to use, but technically all 3 work. You could use all of the voltage that you have available, in this case all 6 volts, but then you'd have to divide by all of the resistance that was available. And that's actually what we did. So down underneath here I'm going to put in the specific numbers. We saw 1.25 amps flowing. You could use everything for voltage and everything for resistance. I like to just call this the everything calculation, right? All my voltage, all my resistance, and I get that correct value for current. Another option, if you have the values available to you, would be to take the voltage on the outside divided by the resistance on the outside. Well, the outside voltage is called the terminal voltage. We already know it was 5. So you could take that 5 volts and divide by 4 ohms for the light bulb. I like to call that the outside calculation. Had you known those numbers at the beginning of the question, you could also have found the current to be 1.25 amps. Now, we didn't know the 5 until we knew the 1.25 amps, but technically that does work. The other option, pretty rare, but I guess it works. You could talk to the Girl Guides and say, hey, how many dollars are people spending, and what's your resistance? And you could do what I call the inside calculation, a 1 volt drop divided by 0.8 ohms. So you've got lots of options there for finding the current. Now, one final thing. On your formula sheet, you'll notice the equation doesn't just say EMF minus IR. It actually says EMF plus or minus IR, suggesting that there might be a situation where you would actually be adding, you'd be maybe adding 1 volt to the 6 and saying, oh, the terminal voltage is 7. And so you start to look at that and go, how could that ever happen, that the voltage from door to door in this bank would be 7 when I'm having a $6 transaction at the actual teller? And the answer is, it could happen if you run this bank in reverse. Instead of taking money out or energy out of your battery, what if you were trying to put the energy back in? What if you were trying to actually make a deposit into your account? If, because of the chemistry, you had to make a $6 transaction at the teller, whether it's a withdrawal or a deposit, and if you knew the Girl Guides were there and they want $1 from you, they're going to want $1 whether you're going one way or the other. They're going to sell you the cookies. So if you go backwards and you go in the outdoor and then buy the Girl Guides, you better have $1 ready to buy some cookies. Then you'll still have your 6, and then you come back out the indoor with nothing. And so there would be a time when you'd have a 7 volt door-to-door terminal voltage. So let's look at one last example. Let's look at charging a battery where you're just running the current backwards through the battery. I have 2 batteries here. Battery A is a little stronger for voltage. It's got a chemistry voltage of 8. It's going to drive the electricity the traditional way, but now in reverse through battery B, which is not as strong. It's only 6 volts. And I have a 7 ohm resistor up in the top there just to keep things slow so that I don't charge this too fast. I don't want anything getting too hot, so I want to keep my currents nice and low. So battery A is running normally, and battery B is being recharged. For battery B, I'm going to need to use that equation in reverse with the plus sign on it. So going through this story here, the current is going to go out of battery A and then backwards through battery B. It's going to come out of the positive end of A, and it's going to be forced the wrong way through B. Now the total resistance facing this electricity is going to be 1 plus 7 plus the 2. It's a big series circuit, so it's 10 ohms. And I now want to figure out how much current's going to flow, but we never talked about this in Physics 12. This is brand new to us. How are you supposed to do Ohm's law with this? Should I use the 8 volts and the 10 ohms, or should I use the 6? Or do I use 14? And the answer is none of those. It turns out the 8 is fighting the 6, and it's only 2 volts better. So we actually take the 8 and subtract the 6. There's effectively 2 volts pushing, and it's got 10 ohms of obstruction. So the current's actually pretty low. It's only 0.2 amps. And now you can go and exercise these equations. Battery A is being used normally. This is the most common use of this equation with the minus sign. Battery B is being recharged. It is the only time you put the plus in there. Okay, and now just offering the values in. What we're going to find is the terminal voltage for battery A, it's not 8 volts. The electricity received its 8 volts, but it actually lost 0.2 volts just getting out the door. So the electricity leaves battery A with 7.8 volts, and as it arrives at battery B, it's already spent a whole bunch on that 7 ohm resistor. In fact, it spent 1.4 volts. But as it arrives at battery B, the door-to-door, the terminal-to-terminal voltage is 6.4. That 6.4 volts can go in the battery. You're going to end up spending 0.4 volts on that internal resistance, and you'll still have your 6 to recharge the battery. So only for batteries that are being recharged will you see this equation written that way with a plus sign. It's very rare. Most of the time, 99 times out of 100, we're going to be just running the battery normally, depleting the energy that's in it, and we'll see that it's EMF minus the loss to the Girl Guides, minus the IR. And that is the last lesson, last little bit of the lesson for Chapter 6.